Fine. So let's start. So let's start chapter 2. So chapter 2 is basic computer organization. That means previously in chapter 1, we have discussed about the levels, the overview of computer. That means how the computer is working step by step, level by level. Because in chapter 1 we have discussed level 0 to level 5, that is 6 levels, and user view also, how the user can see the computer from the outside part, right? But in chapter 1, we are now we will learn about more closely about the computer, each basic components. Previously, we were thinking about as a whole computer. Now in chapter 2, we are now concentrating on individual components of the computer. All right, individual components of the computer. And we know that basically we have 3 basic components of computer, right? One is processor, and then memory, and the last one is the input-output device. And all these 3 are actually interconnected with each other by system bus. That means the bus. Okay, we will also discuss about the system bus just after some of the slides. So let's see some of the very basic thing about computer architecture and organization. So we actually have 2 terms. One is computer architecture, another one is computer organization. Both of them combinedly together and have a system. All right. So let's see what is computer architecture. Computer architecture is, as you can see, is a logical aspects of system implementation as seen by the programmer or the user. That means it's actually a logical aspects or logical view. That means how you design your computer, how you design your processor, how you design your system or robot or something else. So whenever you think about any architecture of a system, you always visualize that, okay, architecture means the logical aspects. That is how we design it logically, hypothetically, theoretically. All right, and this this logical aspects includes. Look, there are some example. Instruction set, the format of those types of instruction, types of the data you are using to do all this instruction, and the type of the addressing mode. Okay, so we will discuss all of this in the very recent future, one by one. So I hope you understand that what is actually an architecture of any system. So architecture means logical aspects or logical perspective or logical view of any system. Okay, if you think about in general about computer architecture, look at the last line, third line. Computer architecture means how do I design a computer? So it's all about designing thing, logical thing. All right. So if you think about architecture of the processor, you will think, okay, how the processor is designed theoretically or logically or hypothetically, right? But if you think about the computer organization, it's completely opposite. That means it's actually encompasses more on physical aspect. That means if you think about computer organization, that means we think that, okay, physically how the computer actually works, that is actually computer organization. For example, how the circuit is designed in our motherboard, how the control signal passes from motherboard to the RAM, how the types of the memory we have, how many memory we have, what is the structure of the memory. So this kind of thing, physical thing, is actually considered as computer organization, right? So if you think generally, again, the same way, look at the third line. It says that how does a computer work? Fine. So that means architecture means how we design a computer, and computer organization means how does a computer work itself by physically. So that is actually the basic thing of architecture and organization, and we mix together. We actually combine together the architecture and the organization combine together to build any system. Because let's say, for example, you want to make a robot, right? You have to design it first. That means you have to make your architecture first. You have to design your how actually they will connect each other, what will be the instruction for doing this and this, what type of data my robot will process, how we can communicate for each of the communication line, all right, how we can do that. So these are all planning, right? That is all planning and designing. So that is the architecture. Physically, when you try to make it work, your robot, that means which circuit you are actually need to attach, which signal we actually make it connect to each other so that they actually can activate the sensor, which type of device or other types of memory we actually try to insert it so that it can move faster. So something like that. So it's related to the physical aspects. So I hope you understand the computer architecture and computer organization. Right? Okay. So let's see another very important and very interesting principles. Look at the red line, the red text, what is written. Let's just read 30 seconds, then I will explain. This is all about principles of equivalence of hardware and software. That means theoretically or hypothetically, you can do any task. Same with the hardware and also by the software. That means if you can do one task by software, you can do the same task by the hardware, and vice versa. That means if you can do anything by the hardware, you should be able to do the same task by the software as well. But there are some conditions. As you can see, there is a star. So the star means you have to consider something. You have to consider some of the scenario. So first of all, first thing is we have to assume that we don't consider or we are concerned about the speed. Sometimes if you do only in the hardware, it is much more faster sometimes rather than doing in the software, or maybe opposite also. So the speed actually should not be a problem. Okay, one thing. Second thing is very important one. Second thing is to understand this principle is at the bottom line. For example, you are writing some software, right? You're writing some software. You cannot write the software on the pen and paper and it will work, right? You have to use it in into a system. So you can write software are just instruction. So you can write the instruction into a system, but at the end, at the bottom end, there must be some hardware to implement those instructions from the software. Okay, so we are not considering the bottom level where must be some hardware. We are thinking about a little bit upper level where software giving some instruction to the hardware so that they can do it, and also we can do the same, we can give the same instruction to the hardware by the hardware so that it can be done by the hardware. Let me give you an example. I hope you'll understand. Let's say, for example, I have a printer. All right, I have a printer. I want to print something. Let's say I want to print one page. So according to the theory, I am able to do the same printing job by using a software and also by the hardware. Okay, only then we can see that okay, it's actually the software and hardware is equivalent. So how we can do it? Remember, printing the page is our task and it should be done by the printer, right? But the controlling the printer or sending the instruction to the printer so that they can print, this instruction can be given by the software or can be given by the hardware. That is actually the equivalent we are talking about. We are not talking about that printer is printing a page, but the software cannot print a page because it's a hardware thing. We are not thinking about the lower level. I told you we need to consider that in the lower level, we must have some devices which will execute the instructions. All right. Think about the volume control. This is actually given by the other student. I like it very much. Let's say you want to control the volume into your speaker. We actually can do it two different ways. We can use it a software, right? We can use a software to decrease the volume of my speaker. We also can use the hardware itself so that we also can decrease the volume. That means we are doing the same task by using either the hardware or the software, or can be both. That is the equivalence. Third example for you, for better understanding. Let's say we want to add two numbers. Let's say we want to add 1 and 5. Okay? We can write a C code or any other code to add these two numbers. We can write this code, compile it, and then we can have our result. So we can do the summation. We can do the same addition by using some of the hardware. Let's say we should have one or two AND gate and OR gate and some other gates and a microcontroller so that we can have somewhere we can easily can make an adder by using only the hardware. We don't need any software to do the addition. So this is just an example. If you can do the task by the software, you should be able to do the same task by the hardware also, and vice versa. This is the principle of equivalence of hardware and software, and it is true for every situation. But we need to consider, as you can see, there are some there is a star mark. That means we need to concern, or we need to assume some of the scenario. First scenario is we don't consider about the speed, either hardware is faster or software is faster, and we don't consider that at the bottom end there must be some hardware to implement the instruction given by the either software or the hardware. So we should consider these two things. Only then the principle of equivalence of hardware and software will be true. Okay, I hope you understand. Any question? Oh, by the way, can you give me anyone a little bit more example if you understand this principle? If you understand, can you give me one more example? Anyone?
Sir,
That,
can
that
calculator be an example of the whole concept? Like we are typing 1 plus 2 and
uh-huh.
it is giving a result, but
Okay.
calculator is an hardware and a software in a both way.
It's actually, yeah, it's actually both, because inside it we actually have some language so that it can work together. Yeah, you cannot give this
Seems
same
like it's,
example. Yeah,
yes, it's
for the
complex,
adding
sir.
thing, for the adding or mathematical thing, you actually need to separate hardware. For example, some logic gates by which you can do the adding. Whenever you are going to do the DLD course, digital logic design, you will do this type of thing. You will make adder, you will make subtractor, you will make multiplier physically and with a device like a calculator. So you will do it in the DLD course. So it can be done. It can be done by the hardware. Only the hardware. You don't need any software. Can you give me any other example? Because other sections actually give me very good example. For example, this speaker example is given by the one of the student. Can you think about any good example? By the way, you can give example only when you actually understand the principles, or you can ask me question if you have confusion. Think, think, think about it. Try to look around you. Let's think about your mobile phone. Let's think about your printer, your computer, your monitor, your CPU. Think about it. That is it. Are you convinced that yes, what is sir is saying, or what is the principle is saying, that hardware is and software are equivalent theoretically? Let's check.
Sir,
So you actually can check yourself.
sir, a mobile phone touch screen. Actually, touch screen is control.
That skin.
So touch screen is controlled by the software, and the instruction the software get from the touch screen is processed from the hardware.
Mm,
Sir, web
not
camera.
not entirely.
Sir, elevator can a principle of.
Elevator.
Yes, sir.
How?
So we give the instruction which floor we want to go, then we have to press the button and
Yeah, if it is press the button, that means whenever you press the button of the lift, it's actually combination of hardware and software both.
yes, sir.
By the way, generally all the system, whatever you are using, is actually the combination of both hardware and software, right? It's combination of both. But I'm asking you the example that this is what this task is work entirely by the software, and this task is entirely doing by the hardware. Can you find this any kind of task? Whatever
Sir,
your example is all about the combination of both. Yeah, try.
sir, I have example that my mobile phone lock button, I can lock it with a button and I can lock it with two touch on the screen.
Exactly, almost. Yes, almost. Although whenever you're touching, yeah, so somewhere it is correct. Whenever you're touching, you're also using some hardware. But yes, in some other perspective, it is correct. Yes, whenever you have to put the button, or you just press using the
Sir,
software.
we can shut down our PC by going to the start button, and we can shut down by PC to the
Exactly,
main.
exactly. Very good. Yes, you can shut it down by using the button here, or you can use just the software here. Yes, correct. See, you are start understanding the principle. Yes, correct. That
Sir,
means starting down. Yeah. Sumaya.
sir, car indicators, when we sir indicate it, we use the button, and when it's turned, then it's automatically off.
There is no, there is also the combination of both. combination of hardware and software both. Because there are something that there are some in that indicator, there are something that whenever you move your wheel, is actually there are something which cancel your indicator. That's actually combination of both. Okay, one example is given by the other student. I really like it. For example, the monitor. Let's say if you want to change the brightness of the monitor, right? You can do it by the software and by the hardware, right? You can change it by using right click and go to the display and you can change it. You also can change it with the physical button of the monitor, right? So you can do the task, same task by using the software and the hardware, same task.
So it's like our TV set. We can turn
Yeah,
on the by remote, and we can turn on by touching the start button.
I hope you understand. So that is actually the equivalence of our so it's fine. So you understood. So I'm very happy. So let's go to the next topic, which is previously we just see our computer as a whole like this, but now, as I said, in this time we are going to discuss more about components of computer. That means we are going very close inside the computer. That means how does it look like, and how the architecture of it, and what are the principles of working. So if you can see the computer here, we see that we have three basic components: input output, main memory, and actually main memory, not main memory. Memory and CPU are a central processing unit, or you can say the processor. And three of these main components are connected together by using a system bus or interconnection. This is a one kind of connector. It's called bus. That means there are three types of bus. We will also discuss that about the system bus. That means how they interconnected each other. So these are the basic components of our computer. That means our processor, our memory, and our input output, and they are connected each other by using the system bus. Okay, so that is our computer overview of computer. But if you go more closely to the CPU, we actually can see this one. Go more closely to the CPU. So if you go close to the CPU, you actually also can see there are another three components inside the CPU, which is of course ALU. I hope you know what is ALU, right?
Yes, sir.
What is
Arithmetic
it?
logic.
Arithmetic
Arithmetic
logic
logic.
Arithmetic
unit.
logical
Yes,
unit.
correct. Yes, correct. So this is the arithmetic logic unit that we calculates those calculations inside the processor. We have some controlling unit which can control the CPU and some registers. We already know that what is the register. That means there are some small. This is the smallest memory we have in our computer, and internally, of course, we have some internal bus. Okay. Do you remember whenever we say the registers, I show you the memory hierarchy. Do you remember memory hierarchy? I show you one pyramid. Remember?
Yes, sir.
Yes, sir.
So on the top of the pyramid, do you remember what is in the top of the pyramid? Register.
The register.
Register,
Register.
yeah. Register is the fastest one, fastest memory. After the register, cache.
Cache.
Cache is the next second fastest one. Third one,
Then the main memory.
third one
Main
is our main
memory.
memory. Yes, correct. Third one is our main memory. After that is our hard disk.
Higher, sir.
Our hard disk. Fourth one is the hard disk, and the fifth one is our CD, DVD, or Blu-ray, or that means our optical device. And the last one is our tape drive, which we don't use it now. So that is the memory hierarchy. That means the fastest one is the register. So that is actually the register, okay, inside the CPU. And I hope you know that already, that whenever you write the assembly language in the RISC type of processor, they're actually using this CPU register. Remember, we have given some example that $sign T1, $sign T2, $sign T3.
Yes, sir.
These are actually the registers inside the CPU. And CISC processor is actually using the memory, not the register. So those things we will discuss one by one. By the way, each of the component, whatever you are watching now, we will discuss one by one. Okay, you might thinking then why we need to know that much? Because we are doing coding. We will do coding. So whenever you do the coding in C or Java or any other language, you don't need to consider anything. You just do the coding. You just know the syntax. But why we need this one? Because I told you that whenever you try to write in assembly language, you have to have a very good understanding of your system for which you are writing the assembly code. For example, if you have a robot, you build a robot and you want to write some code. If you don't know that what are the components of the robot, if you don't know what is the architecture of the robot you have made, if you don't know how they connect each other, you cannot write a code, right? So the same thing. If you have a system, if you have a computer, and if you want to write a assembly language to do some tasks, especially related to the assembly, hardware, you must know the architecture and the structure and the organization of the computer. That's why we are all need to know all this. So if you know all of them better, it is very easy for you to write the assembly language. Without knowing this, that is absolutely sure that we cannot write assembly language. Okay, so that's why we need to know. By the way, if you go more closely to the CPU, you can see that control unit actually also have basically three things: some of the logical part, some of the control memory, and also some decoding and some registers. Okay, so that's how we need to see now to our computer. Okay, previously we saw the computer as a whole, but now we will learn more deeply about each of the component of the computer. Fine. Okay, so we will discuss 5 more minutes, then I will give you break. After the break we will have quiz. Let me just discuss 3 more slides, then it is fine. So very shortly, we know that our processor is the first and foremost important part of our computer, and we know that processor is the only part where we actually execute the program. You know that program is the set of instruction. So the processor is the only thing we actually can execute the program or instruction. And we know already these two things: architecture and organization, right? So if you think about the architecture of the processor, then of course we know that we design or we determine that how the sequence will come one after another, and how we are going to execute, how we design our processor, what are the instruction set, what are the data type of the processor it can handle. So these are the things is very considerable for the processor. If you think about the organization of it, of course it is the hardware part. That's why we think about how the register is working, how many registers we have, what are the name of the registers, what are the location of the register, how they interconnect each other, how they work into the circuit. So that is the organization of the processor. By the way, we will discuss also in this chapter every single thing one by one. Right, this is just a picture, very simple one, and I think it's very self-explanatory. But you can see that if you enlarge or if you go inside the CPU, we can see this, and you already know that you have a register, not one, several registers, our ALU and our control unit and internal CPU interconnection, of course, because otherwise they cannot communicate each other. Okay, we will discuss also. The second most important part is or component of the computer is the memory, and we know that in the memory is a physical thing where we need to store our data or instruction. By the way, in the memory, it actually can store both of it. That means you actually can store the data which can be needed for executing any instruction, or it can be store the instruction for the processor, because it's waiting into the memory so that the processor can come to the memory and fetch the instruction and then execute it. So before the execution is actually into the memory. Okay, so memory is actually a very important part. That's why if your memory size is bigger, then the performance of your system will be much better, because memory is faster, right? Memory is faster. So if you have larger memory, that means you can store larger amount of instruction, and is for the processor it's easier to get and fetch the data and the instruction from the memory rather than the hard disk or rather than the optical device. That's why we must have a larger memory so that we can store more data, so we can do more tasks. Okay, these whatever is written here is all about theoretical thing. We already know that. Okay, so that is the memory. And the last part is the input output. We know what is input output. That of course without an input output, the memory cannot have the data. Without input output, the processor cannot give the output or cannot give the result to someone so that it can be seen by the user, or user cannot interact with the system, with the processor, without having any input output device. Okay, so input output, of course, is one of the important parts of our full computer system. Okay, although it's written so many things, it's all about the theoretical thing. We know already. Let's say, for example, the input output analysis define the structure of an subsystem, how the functions are distributed between element distributors between elements, and various speed of different elements. By the way, okay, this little thing, it says that the various speed of different elements. Okay, I hope you know that whatever you are actually connected to the device, either it's an input device or output device, all of the speeds of that is not same. The speed of interacting with the mouse is not same of the interacting of our speaker or maybe our laptop. So we actually have different speed of we have different devices of input output which have different speed. So you also need to manage and organize these things. Okay. By the way, we will discuss very elaborately in this chapter number 2, at the end of the chapter number 2, about input output. So that is actually overall description of our computer system so far. Okay, do you have any question before we start to the do you need anything, any question?